Hi, everybody. Welcome to our second lecture this week. We want to finalize our considerations about the generalized modeling, in particular, the way how we glue the different elements together. Yesterday, we learned how to generate the equivalent circuits for different domains. So again, this is not the basic way we do if we look at professional tools, because there you find the different pictograms, but it somehow shows you what is necessary if we want to build something which is consistent and works in these tools. Second example, with a quick view yesterday, this kind of hydraulic pipe system, phase safe hydraulic pipe. The pipes are here, 3 and 4. And the modeling of the pipes is now depicted here on the next slide. So first of all, you see the different gyrators which transform mechanical position, velocity, and for force and velocity into a pressure and volume flow on the one hand. Due to the fact that there is a mechanical connection also to the secondary side. So basically, if we go from here, there's also a mechanical connection over here to the second piston. You find something like this inductance here. There's a spring in between. So piston 1, spring, piston 2. Here's the force. One part of the force is transformed into hydraulic volume flow sensor, and the second is directly transmitted to the second piston. That's the point. So understandable here. And this is the last spring, which is attached to the environment, so basically ground in electrical engineering. And you transform this again into a volume flow. So what we need right now here is the pipe modeling, and here it comes. So first, the pipe. Usually a pipe itself is transportation of mass through the pipe, and you have friction, obviously, in general, if the pipe is if you have a lengthy pipe, also you find something like a resistance or dissipative element and an inductance for describing the volume flow. This is the very same for hydraulics, whatever you look at in cars, the safety valve, and or if you want to model your garden watering system, something in that direction, you find usually this inductance resistive relation. And then you might ask, what is the capacitance here? Well, this is due to the fact that there's here, you find here some sort of a chamber, which is well, squeezed together, meaning, oops, a couple of people are entering the room. Welcome. And this can be easily modeled also by a capacitance. This is something which we did not deduce by physical relations directly, but you'll find this in Wellstedt's books and then others, that if you not have a classical tank like a cup of coffee, but just a tank which is a pressurized tank where the volume is always the same, but you change the density in between because you have compressible liquid in it. This is the very typical situation in many technical applications. So therefore, here you have a chamber and there and there and there also, here and here. So finally, you find something like this capacitance. This is the most simple model of such a thing. So at the very end, you find these two capacitors and also C3 and C4, what I mentioned before. And opposite side, you find again a direct mechanical link. Then the hydraulic to mechanical, which is over here. Then again, mechanical to hydraulic and hydraulic to mechanical. So there are various options to put the gyrators. So this is not the only way to position all the two port elements as well as the one port. elements. So there are various possibilities. So it's not unique, so to say, to model such a system. This is quite, well, this is a knowledge you already have. We know we have different kinds of models. And one interesting fact at this point I want to mention is you have directly in your hands the abstraction level you choose. In particular here, well, I have a very simplified view of the pipes. I have a very simplified view of the chambers. I have a simplified view of the transformation principle. So in all these steps and all these decisions you make, you can choose it differently, depending a little bit on your application. And if you want to get a certain, well, overview, for example, for just understanding the basic principles, I would say even without friction would give you a first idea what happens, how many storages are there, what is the order of the system, something which we want to tackle today, and all these things. That's important to know. And here we are with the electrical system, a little bit more complex than the one before, but well, quite intuitive on that side. Well, what you need if you want to do it very often, then it's important to practice. Unfortunately, I have to say this. So it's sometimes a little bit strange to model the capacitors, in particular for mechanical systems. So we are not used to do that and to connect these capacitors and masses somewhere on ground. So you have to learn it in that sense. And the only way, well, that's the bad news, is to practice. So take anything you have in your mind and try to model it with an equivalent circuit. So to get used to it, that's all. So after a while, you're, well, familiar, and you will not have any problem to model these things. What is interesting, in addition, perhaps back to our example here, I wanted to mention, well, here we talked about this, well, oscillator, which is included here to damping down the various frequencies or eigenfrequencies, which are given for the shaft and which are safety critical because the shaft can break. And due to this fact, we introduced this red encircled element on the mechanical side. Well, I want to highlight when I first started studying these things, these equivalent circuits, and started to learn that, well, okay, the mechanical story translates directly into electrical engineering. This is wonderful. So I can also transfer electrical engineering knowledge into mechanical objects, more or less. So in particular, in filter theory, I mentioned this yesterday, then, well, why not transforming more complex filters into mechanical objects? So trying to find mechanical objects which perform the same filter technology we have in electrical engineering. And there's one hint I have to make, or one, well, big remark. Not everything can be transformed. And the question is why? And there's a big difference to what you know from electrical engineering. So a lot of things can be transformed, but not everything. What might be prohibiting or will make it difficult to transform everything? What is special for mechanical objects, for mechanical equivalent circuits? There's some speciality which we do not have if you look at, well, electrical engineering in circuit design. Can you place every element everywhere? Everywhere in between two nodes? Yes. That's it. So only those, they have to go to ground due to the fact that we want to measure it to inertia, to inertial system. That's important. And if it becomes really complex and or difficult if you try to position a mechanical condensator or capacitor somewhere in between two nodes, where one is not the ground, because then you have to define the different relations between the different nodes, effort variables. This makes it very, very complex. And so there's a certain relation which relates uh, um, the inertial system. So if we take it as a rule, say, okay, capacitors have to be grounded, then obviously capacitors between two electrical nodes are not possible in mechanical engineering. So every circuit, you know, from circuit theory, where a capacitor is in between, which we know there are circuits where the capacitor is in between two nodes, can't be transformed in mechanical engineering domain, and that makes it a little bit more difficult. On the other side, if we look at hydraulics, there we don't have such a rule in that sense. So in hydraulics, we find almost everything in the hydraulics domain, what we know from electrical engineering, or if not even there, then it will be there. But it looks a little bit, 2 weeks ago, I visited a research center in Copenhagen. I think I mentioned this already, and there they produce a test field for district heating grids, and there everything is connected. And if you try to build really complex circuits of district heating grids in terms of their interconnection, and it becomes a little bit looking like the first computer built by relays also. So really, really difficult structures. So building something like a microcontroller will be difficult in district heating networks also. That's perhaps the message, that because you have a tool valve which has a certain dimensions and therefore, yeah. But on the other hand, we can transfer something in that direction, and therefore you find something like the step-up converters, step-down converters, and all these nice things we know from electrical engineering. So for the basic understanding, it's very helpful. And for me, it was helpful also in practical life at BMW to understand, because I was responsible for a braking department with advanced braking. It's more software side, advanced braking system. So brake-by-wire system, all these things, but also disc brakes. Well, this is classical mechanical engineering. I had really problems at the very beginning to understand what they are doing. And this helped me a little bit. Okay, this is the electrical engineering side, and now I want to give you an impression what results. Well, if we look at electrical engineering, so now we are in our domain, we know what we do. We are doing, right? So at this point, we have capacitors, inductors, inductances, and gyrators, transformers, and all these things. And then we can do our nodal analysis, also our circuit laws, Kirchhoff current law, Kirchhoff voltage law, write down the nodal equations, the loop equations, and also the element equations for the differential equation, which is governing the behavior of an inductive relation given here, or capacitor given there. So if you glue all this together and write it down in a ordered way, you get just simply saying something which looks like this. So a set of equations where you have derivatives in it, a set of equations where integrals appear, a set of equations where you have just algebraic relations. And in vectorized notation, so stapled all together in vectors, it looks like this. This is the very basic thing. And if we just look at linear system, which we have, what's this? Okay. Sounds strange. Okay. What we have here, linear relations just, this means, I have a linear relation for inductance, a linear relation for resistor, I have a linear relation for a capacitor, and also for gyrators and transformers, etc. So if we glue this together, we can derive all sides so that at the very end, all derivatives disappear. So every integral can be derived once, then you get just an algebraic relation. Second time, I get, so as you know, you can always write the relation for inductance by means of an integral or a derivative relation. Once on the one hand side, you calculate the current, other side you calculate the effort variable. So it's always the same. So at the very end, it looks like this, and this is similar to what we know from state space theory. And but one little thing is different. This is this matrix E, which is in front of x dot. So if we boil it down at for linear equations, then we end up with so-called differential algebraic equations. So you have in parallel algebraic relations and also differential equations. And this is a little bit more difficult to solve, in particular if you look at numerical solvers, because a numerical solver has in parallel to solve the differential equation and be sure that the algebraic relation is also fulfilled. That's the story. So what is the framing? You said, okay, solving differential equations, that's well known. And in addition, only those solutions are allowed which are fulfilling the algebraic relation, relating some of the variables which we denoted by x. So this is what is the object of interest for the numerical numerics guys, for the numerical solution of such things. But I can tell you, you can ask there exists a set of solvers which are capable to solve these differential algebraic relations, and therefore simulation works for, well, this kind of directly circuit equivalent circuit things, or if you put other pictograms like pipes, etc., in front of it, also for other representations. But it's quite simple. You end up with these differential algebraic relations, and in some cases, not all, but in some cases, this matrix E is non-singular. Singular means you have an eigenvalue equal to zero, which means the matrix E is not invertible. But in many cases, I would say, in many cases, E is non-singular, so it's invertible, it's another word. I can represent it in this form. I invert the matrix E and I get, this is nothing else what you learned in the first semester, but I think Mr. Dösse was the guy who taught you linear electrical networks. He never wrote it in this form. He always wrote the equations down and said, now solve it. And sometimes at some point, yes, I put this in this equation, this and that equation, this and that equation. And after a while, yes, it's so easy. Well, it works like this. And in a more general form, you always deal with such kind of object, where you did some sort of inversion, but by step. It's like handy inversion of a matrix. And that's given here. Okay, so at the very end, you end up with x dot is equal to e to the power of -1, a tilde x of t. And now we are where Mr. Kluge starts, with a state space system. And now we know what's inside the state space system. Obviously, some sort of states, yes, okay. Some variables. I have never said something like, well, states, we have to define what states mean. Comes on a few slides later. But at the very end, we end up with such a form, such a structure. It's A times X plus B times U is equal to X dot. This is very natural, and this stems from the fact that every system can be represented by this lump parameter system form. So now a state space description, you might ask for, why is it a state space or this specific structure? Here's the answer. Okay, so it makes very much sense to say it's not a Laplace transform with which we start in system dynamics and control in the bachelor. No, it's this one. So that's the physics. And we know, okay, the x dot, who's responsible for x dot? So the dot in the equation in the first here, who produces derivatives in the relations? Which kind of elements is the question? physical elements. So if we look here at this example, who's responsible for the dots, the derivatives? Yes. The inductor and something else? If we put everything in derivative form, who brings dynamics into the system? Capacitor, right. So capacitor and inductor. So these two guys are responsible for our dynamics. Oh, here we are. So for x dots, responsible are our storages. Now we are close to what you learned somewhere else. So the storages are somehow responsible for the track. But there is something which we should be careful of, or we should take care of, better to say, it's E. So E must be invertible. So sometimes might be not invertible. So let's have a look. What happens if it's not invertible, and under which conditions? And that's perhaps the question. Sometimes there might be a what does it mean that there is something not invertible? What does it mean mathematically? If a matrix is not invertible, what does it mean? Just mathematically. Yes. Oh, sorry. Let's see. Yeah, it's okay. It's okay. There are a lot of questions today, so there's room for others. Yeah, might be series or something else. Yes. Yeah, but it's not invertible if it's not invertible. No, I mentioned if it's not invertible, what does it mean? So I think in the last row was first. Yes, please. Couple of solutions. Yeah. Determinant zero also. Thank you. And there's some. Yes, and some of the equations are what? Dependent. So they are linearly dependent. That's it. So you multiply one equation, you can cancel one out. So what does it mean physically? If you can cancel one equation out because it's redundant. Exactly. So there's an example I want to give. If two capacitors are connected in parallel, so if you have, for example, such a equivalent circuit, which looks like this, well, how many variables do you need to describe such a thing? Just one for one capacitor, because the second can be directly derived from the first one, and vice versa. So they are linearly dependent if you know the capacitance. If you don't know the capacitance, then it's not possible. But if C1 and C2, sorry, I have to add it. If C1 and C2 is known, I can calculate the charge relation between the two. So obviously, if E is not invertible, we have a case that some of the storages are dependent to each other. So the question appears, under which condition are some of the storages dependent? I don't know whether you treated this in linear electrical networks. It happens. So you learn it and, wow, sometimes looked a little bit strange, but yeah, we checked this. Okay, but key takeaway is, okay, E might be, it's not the only case, but it might be the case where there we have dependencies in for example, storages which are there. So we need not all the storages. And here's the problem. If we talk about state space systems saying, hey, the states are completely defined by the storages, that's not true. Because you can have such a situation where two capacitors are connected in parallel. I do need just one state to describe the entire system. And therefore, just to make an example where this is not the case, where we have a very simple situation where everything is needed, well, here an oscillator circuit with a dissipative element, if I do the calculations, Well, according to Kirchhoff's law, we get the voltage drop across all closed loop such that it equals to 0. So U1, UR, UL, UC. If I sum it up, I end up with this. If I do the first order derivative, I end up with an equation which looks like this. This is just write it down as it is. It's nothing else than Kirchhoff's laws. So, and here we are. There's E. Here's E. Sorry, E. A tilde. And B tilde. And obviously, if L is not equal to 0, then we get an equation which means that I can invert this matrix. If L is not equal to 0. So then it makes sense. I can write down the state space system, and I have two storages which have to be described to describe the entire system. That's the way. But what we introduced are two variables, x1 and x2, which we call states, because these two variables are needed to describe the entire behavior. Without, if I leave one out, I'm not able to describe the entire dynamic behavior of the system. And therefore, the typical state space description is a little bit circular, I would say, because, well, I define state space variables are as inner states. Inner states means, well, inside a box. And these inner states of a dynamic system such that the dynamics of the system are fully described. Fully described means that every value of any effort or flow variable can be calculated out of it. This means fully. So every value of every effort or flow variable, this is always, again, a little bit not well defined in the bachelor degree or first master lectures. And if I know the states for one instance of time, I can uniquely describe the rest of the trajectory. So that's what, as long as I know the input values U. So that's a very definition. Well, obviously, that's something we discussed already. Obviously, the dynamics of the system are governed by the storage elements. That's clear. But obviously not all which storages. So what we can say, each storage element describes the energetic state of the system. So energy is the most important part for describing the dynamics. So energy plays a particular role for the next chapter. So keep this in mind. So energy is the very important term. But there might be a situation where these energetic variables are algebraically connected. I mentioned this example with the two capacitors, if they are connected in parallel, but this is a very simple example. How do I find these parallelisms if they are, well, algebraically connected over an entire huge graph where you don't see, or equivalent circuit where you don't see this parallelism? It's so easy. So we need some tool to find out where this parallel connected capacitors or inductances are, which if inductances in this case it's a serial connection. So so the question is, which is the minimum number of energy variables needed to describe the dynamics of the entire system? That's the first step. So we know from a theoretical point of view, there might be variables which are somehow redundant. And if they are redundant, we do not need them because they can be described by only one of them. So that's basically the problem in question. And there exists a wonderful way to do that. If you ask, perhaps you have friends in the mechanical engineering domain and they learn something in that direction, They learn to define mechanical system to find the redundant coordinates, non-redundant coordinates, non-redundant system variables. That's their task, and it's something you have to learn if you don't learn these kind of things. For you as electrical engineers, quite easy to find this for these kind of circuits we look at, for these non-redundant or redundant systems, and this information is entirely stored in the graph of the equivalent circuit. That's an interesting fact. So if you know the graph, if you can look at it, it's obviously a topological relation between some of the capacitors, inductances. That's what you saw before. They are somehow connected in parallel. So we should find out what is in parallel, or how many variables do we need at the end. And this is the so-called shortest connection network, what we want to construct next. And we need some abstractive notation first. It's called the spanning tree. A spanning tree of a kinetic unidirected graph contains all the nodes of this graph such it contains no loop and is connected subgraph of G. The spanning tree with k nodes contains k minus 1 edges. All edges of the graph which are not part of the spanning tree are called links or chords. Spanning trees can be determined through depth or breadth first search algorithms. You might remember this depth or breadth first search algorithms are very popular in informatics. So for you, it's easy to program it. So finding spanning trees is simply to implement in C, Python, or whatever you like to do to use. And let's have a look at this. Let's abstract the things. This is the original graph. So in between two nodes, there might be an element, for example, a resistor or a capacitor or something. And the problem in question is, now let's construct a spanning tree. And first it's not unique. There are a lot of spanning trees, and I give you some here over there. The idea is you have to connect all nodes without closing the loop, which is obviously given by the red graph. So if I just put here one connection between two nodes, then I close the loop such that I can circle around in one part of the graph. For example, if I do it, so I'm not using red color, but perhaps blue. So if I close it here, I can circle it here around. That's what I mean. So just if I add one additional edge, connection between two edges or link it, then a loop exists. Now the interesting fact is, if here, for example, equivalent circuits with k nodes, red the spanning tree, green the links as given. And the interesting fact is we have with the spanning tree the number of independent nodal equations at the very end. So with the spanning tree, I note how many nodal equations are necessary. So the number of meshes and nodal equations equal the number of unknown branch currents. So that's it. And then I'm happy. So with that, I know how many independent variables I need. Perhaps you might remember this as the mesh analysis from linear electrical network. This is the generalization of it. And so here, as to be clear, we need just for this example, even if we have capacitors everywhere, they are connected. So here and here and here, all capacitors. For example, you just need, even if you have 1, 2, 3, just 1, 2, 3, 4, 5, 6, 7, 8, even if you have 8 capacitors, you would say, okay, I need to, you would say, I need to use 8 states variables, but that's not true. If you look at the number of mesh equations, you just have 5. So the number of independent equations are just 5. And we need just 5 states to describe the system. That's the interesting fact. And with that in our hand, we know how many state variables we need. So key takeaway, the minimum number of variables needed to describe the dynamical behavior of the system is completely determined by the loop currents if, and this is a important if in this loop a storage element is included, because the loop might also contain just dissipative elements, and dissipative elements do not define any state. So the number of loop currents minus the number of loops with just dissipative elements define the number of states needed to define the entire system. So if we start in basic beginners textbooks for what is a state space system, we can say, okay, the storage elements, but not all, but the minimum number of storage elements which are independent. That's the answer for what is a state in physical relations. Second, we know the storage elements always have a physical relation to something. So we find always inductive or capacitive storages. So we should look for these. And therefore, if you look at a physical object and you think in this, you already see the order of the system, because the number of states defines the order of the system, right? So if you look at a spring mass damper system and you want to end up with these, the minimum order you end up with is spring mass, 2 storages. Damping brings no additional idea if it's not parallel connected in such a way that we reuse it, the variables, then we need 2 variables. It's order 2 system. And this can be done directly on the graph. So if you look at the system, and that's why you're control engineers, and if you talk to bachelor students who learn to tackle these things, and you look at the system and say, yeah, it's of order 5, he says, huh? What? And the only thing you do is you count the number of storage elements. You see them directly in front of you. You can say, okay, I have to deal with order 5 system, perhaps, if with a very rough idea of how I model the system. Okay, so that's perhaps something which is important for you. And now you know, okay, that's why control engineering is working, because at the very end you end up with such a message. It's always the same. We have storages, order 1 storages, and these are the basic elements. So the only question is how many, and that's it. And we end up with a state space system. So it makes sense to deal with linear multivariable control, like Mr. Kluge does in his lectures on, do eigenvalue assignment things and states transforms and all these things, because this is to deal with, where is it? Here, the nice objects here down below. If we do so, then we are at the very close point to physics. But you might say, no, that's not true. Physics is here. So differential algebraic objects are much more close to physics, because there I have not this inversion E in between. E makes the problem a little bit more complicated. So if I want to be close to physics, I'm much more related to DAEs. Unfortunately, control theory for DAE is much more complicated than for the state space systems. And but There are some results for DAs also, but nothing what we use in practice to today too much. So sometimes yes, but not a small portion of all solutions. Well, if we look to system dynamics and control of the bachelor, then we do another step. We use the state space system to transform it in Laplace transform and get this input-output relation with the transfer function, all these things, and can do the Bode plot, root locus, and do the design by loop shaping, etc., etc. So all these things, they start here. Okay. Now, well, this is a story which is interesting. So obviously we have some sort of graphical representation of important and relevant information about the behavior of the system. Now we see directly the order of the system out of the graphical relation and the number of storage elements. Much more can be done if we look at bond graphs. So now we do the very same, but instead of using equivalent circuits as a representation, we try to put it in a bond graph notation. Again, sorry to say, you have to train it a little bit. So, but please always follow the rules here. So the step-by-step procedure, then you won't fail in any case. So it happens, it works as follows. You draw the domain-specific graphical representation with the different domains and physical quantities. Then you define again the generalized flow and effort variables, so FL, EEJ, and then you've tried to find it identifying places with equal potential, so effort is equal. So a similar thing as before for the mechanical example I mentioned. Then you determine the generalized network elements and you apply topological rules for the bond graph. And now the procedure, which is most important, you represent every generalized effort variable with a zero junction. And then you try to make visible the voltages over every element by means of one junctions. This makes the bond graph overly complex at the very beginning, but you please do it that way, not to miss something. I give you a simple example where if you see the final bond graph, you would say, yes, I see it directly, but it's easier to do it this step-by-step procedure. And in the last step, you can glue it together a little bit. Then topological rules, electrical systems, each potential except ground is represented by zero junction. This is also something weird about. So ground is not represented directly. So you have to be careful, and this is something you have to learn. For mechanical system, each mass has to be connected to a zero junction. Yeah, well, let's make an example, and I want to show you this simple electrical system to show you the basic elements and the basic procedure. Okay, first I draw the various domains. Now in electrical engineering, we already have our depicted structure. So there it starts. Next, we identify the elements. Okay, we already have the elements, one dissipative element, a second one, a inductance, and a capacitor, and a voltage source, not to forget. And then, oops, we need a red color again. Here we are. And then we identify the nodes. Please do not forget anything. So we find 4 nodes. 1, 2, 3, 4. Important. Important also are the voltage drops, UR, UL, UR1 better, UR2, and UC 2. Okay. And U is given. Now start with the procedure. Associate to each node a zero junction without ground. Important. I check whether I have, yes, sorry, I put it on the next slide because here it becomes a little bit too small. So for every node 1, 2, and 3, I place a zero junction. So first the zero junction here, the second one here, the third one there. I attach here the node 1, so say node 1, node 2, and node 3. Okay. Now I try to and each node is associated a specific effort variable because there a specific voltage is present. Okay. Now I know node 1 is completely governed by the voltage source because U defines exactly the voltage or the effort of node 1. Clear. So what we can say, node 1 is directly governed by a voltage source of U. Now, I want to depict the difference between two voltages. Suppose node 2 has effort variable 2 and node 1 effort variable 1. The difference between the two can be done using a 1 junction. And with that, I can attach R1. Same manner I proceed, a 1 junction can also depict the difference between the two nodes 1 and 2 and 3, and I associate the inductance in between. And here I have this one junction calculates the voltage drop. So with that, I go over here and say, okay, last node, everything is connected to ground. So meaning this voltage obviously defines the drop for R2 as well as for C. And here we are. This is the very simple bond graph for this simple relation. It depicts nothing else than the physical relation we had before. It's just a different language. And due to the fact it's always like language learning, if you don't know the language, it's always a little bit weird and difficult. But if you have learned the language, it would be more easy. So therefore, training is appropriate and important. Now, what we can do, well, obviously, node 2 is just for representing something. Nothing happens here, so we can collect these two due to the fact that the current or the flow variable which goes in goes out here, so we can directly attach this 1 junction to that 1 junction, and then we end up with something like this. And this is not so surprising because the 1 junction, remember, represents a mesh. And if you look directly into the graph, and if you're a little bit trained, you find something here, a mesh, and there 1 node. And therefore, yes, a 1 junction and a 0 junction is appropriate. But if you have a more complex situation, it becomes even more complex, and then you will fail, I'm sure, if you don't train it. So please do it that way. Even if the bond graphs at the very beginning include something like this, which have to, and you need a second step to put it together, never start with that. This is something for the super users. I know some of my, and even for me, I do not practice bond graphs every day. So which means I use the step-by-step procedure to be clear, but some of my research assistants then say, hey, you can do it directly. And I say, yes, but then I make mistakes. And but there are some well-trained research assistants and they can draw the bond graph directly. Why? Because it's not why we are doing this in our research, because using the bond graphs helps to understand structural properties sometimes. And I want to talk a little bit about this. It's an outlook on the next slides. But here you see, well, it's a very simple representation. Well, key takeaway. First, well, you have two representations for the same thing. Obviously, there's a third, a fourth, a sixth. It depends a little bit what program you use. If you use Simscape, it's more related to the equivalent circuit. If you use Daimler, also somehow, yeah, many of the programs on the market are close to the equivalent circuit notation, and some have this bond graph notation. Behind, if you look in the object-oriented programming situation, it's more close to the bond graphs notation. And therefore, I teach it here, because if you look in the interior of these programs and you want to adjust these variables by your own programs, then you have to know that. Okay. Well, first of all, why is the bond graph so interesting? If you remember the equivalent circuit story, has one drawback. If you want to get the mathematical relation out of it, you have to do linear electrical network analysis, what you learned in linear network analysis. It was always a little bit, not so funny. So if I remember, my linear electrical network analysis was painful in terms of doing mistakes. I missed some variables and all these things. So the problem in question is there a procedure which allows to deduce the state space model directly from the given physical object, if there are just topological rules and these things? And the answer is yes. From the bond graph, it's possible. You can draw the bond graph or whatever you like, and at the very end, you can automatically generate the state space model. That's interesting, isn't it? So no hand calculations and all these. No, here we are. Can we calculate the efforts and flows of a bond graph? And the answer is yes. But there's something you need as an ingredient, which is called computational causality. And computational causality somehow defines what is calculated, whether the effort is calculated out of the flow or the flow is calculated out of the effort variable. That's what is necessary. If you look, for example, the resistive element, U is R times E. So the voltage is calculated based on the flow variable. This is one way of writing it down. The second is I is 1 over R times U. So the flow is calculated out of the effort. So both is possible. If you think of a storage element, well, a capacitor, its dynamic relation calculates the flow or effort, vice versa. In one case, you have to integrate. In the second case, you have to differentiate. But both is possible. But if you have an effort source, well, then there is no freedom, right? Because the effort is given. The flow comes out. So obviously, what we need to do is we have to define some simple form of what is calculated first and what next. And there's one definition, which is then can be graphically represented. As you know, every bond carries two unknown power variables, E and F. And what we can introduce are so-called causal strokes. And these causal strokes indicate on which side of the bond the flow is calculated. So which side of the bond means the flow comes out of the corresponding effort variable and vice versa. In contrast to the error of the bond, which just defines the positive calculation of the power. So be careful. Huh? So with that, we find some elements like fixed causality. The source of effort has always a effort out and flow in causality. Therefore, the causal strokes are here. Effort is defined, flow is given as input variables, so to say. And if you have a source of flow, it's opposite. And sometimes this is perhaps a minor remark. If you have nonlinear relations, I mentioned the case of a dissipative element like U is equal to R times times I. This means that you can invert R and interchange the direction of calculation, but you know, sometimes it's a nonlinear relation, R of I, and sometimes R is not invertible there. It's not possible to interchange the causality. So now let's talk about the storage elements. There exists a so-called preferred causality. It's by definition. We define that integral relation, it's easier to manage in terms of numerics than the derivative. It's due to the fact that we use numerics or numeric integrators instead of differentiators. That's the only thing. And if we do so, it's easy. It's for an inductance. We have the following relation: 1 over L, and we integrate EL, then we get the flow. And for the capacitor is we have to integrate the flow to get EC. That's the definition. Well, that's how the capacitance is defined. So, with that, we, and last but not least, the arbitrary causality of resistive elements, if they are nonlinear, they have to be invertible. Okay, so what is also needed, we have to define what happens at the 0 and 1 junctions. So you want to get out the flows. Therefore, the zero junction, therefore, due to the fact that the efforts are equal, therefore the flow, we have one flow in, 2 flows in and 1 flow out. And what is given here. And for the 1 junction, it's opposite. We want the effort variables to be one effort variable to be calculated based on just saying, okay, one effort variable is given by the others. And it's just a definition to manage this kind of algebraic relations with e to the power of -1, what I mentioned at the beginning. If I define this in a bond graph, I don't have to manipulate e, this matrix. So with that, and last but not least, the transformers, you can read it. We have these causal strokes either as well as the gyrators. And now, with that, we can do the so-called causality assignment procedure according to Carnap and Rosenberg. They defined already very early this SCAP procedure with which I'm able to propagate the causality, and if the graph then is all causal strokes are assigned, then I'm able to define a state space system automatically, because all relations are so well defined that at the very end I can insert one equation into another, into another, into another. This is the case when you, during a linear electrical network lecture or exam, when you were happy because it was so easy to calculate. So the first equation fits into the second and the third, etc., and afterwards you end up with a wonderful situation, just inserting equations into another equation, into another equation. The most tedious task is if you have to solve a set of linear equation. This was always a little bit painful, so to say. And if you do causality assignment, you can avoid all these procedures. So what you have to do is you have to set all causal strokes to elements with fixed causality. So you start with the causal stroke always there, where you have sources of effort, sources of flow, or nonlinear relations where the causality is completely given. Then you assign causality to all elements with preferred causality so that you get the integrators out of it. And then you try to propagate the causality through the bond graph and try to avoid derivative causality. And at least you have to finally define the causality of the resistive elements. This is in that sense helpful because the resistive elements are the elements with the most flexible causality. You can put it on the bond on either side. And sometimes this algorithm fades. We look at this in a second. So now there might be causality, there might be algebraic loops. The causalities of several resistive elements are dependent on each other. So for example, if you look here for R1 and R2, you can assign R1 here, then one junction fits here, then you propagate, and this has an effect on R2. And vice versa, if you choose R1 differently, you have to choose R2 differently, exactly according to R1. So you can put R1 effort in or flow out causality, it depends on you. This makes it, you have dependencies between this. Second example, so one example here, causal bond graph. We start with this example we mentioned in our example before. Source of effort. Effort means a flow out causality. We get here our our preferred causality there. Then we have two free, these two. The capacitor is fixed, and then I can choose one, for example, R2, and propagate to the others, and then I can finish and have the entire thing. Everything is fine. I can do the calculations out of it, because always we have a fixed set of equation where I can insert one into another. So homework, please. Do the mathematics behind what I mentioned right now. So write down the differential equations for a capacitor, for an inductor, for a resistor, and then use the definition of the causal stroke, and then you will be screaming for and laughing because it's so easy. You insert, 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 and at the very end, the differential equation pops out. That's the basic idea. Okay. But sometimes some mysterious things happen, and I want to introduce them because they are helpful to understand some structural properties. These are so-called causal paths. A sequence, just defining a so-called causal path right now, a sequence of bonds from one power port of an element to a power port of another element whose causal strokes are at the same end is called causal path. Well, a gyrator might change the situation. That's not that important. So perhaps I put this in brackets here. And just an example down below, I left out the different elements here. So if we start with the causal stroke here and here and here and here, then you see we have a causal situation where there might be where the situation happens where everything is fine, but if the gyrator is in between the causal stroke here, E1, and at this element here is at the same end, so we will have the very same situation. Or from there, here to there, we have a so-called causal path. Okay, so not to be confused, these are two figures, figure 1 and figure 2. And now this is not so problematic, but it helps to understand a mesh. A causal mesh is called where the causal path ends where it starts, just with its element. And now you may say, okay, this might be conflicting. Sometimes if it ends with where it starts, it's a causal path with the same elements, no conflict. If it ends where it starts with different causality, there might be a conflict, right? And a cause, therefore, we can say a causal loop occurs when the causal path is closed and can be run through several times, over and over again. And the mesh is similar to that, but with an odd number of generators. Why is this important? If you know the number of causal loops, you know whether there is an algebraic relation in between. Here, for example, if you have a transformer, a 0 junction, 1 junction, 1 junction, what does it mean? And you have this loop here in between, then obviously, what does it represent? A causal, a 1 junction is an algebraic relation. A transformer is an algebraic relation. A 0 junction is an algebraic relation. If everything is connected, this means, well, I have an algebraic equation in my set of equation. This is a situation where I have to solve algebraic equations. And solving algebraic equations for our models means there is an E I have to respect. Right-hand side causal mesh. Okay. Well, if I want to derive a state space system from a bond graph, now it's easy. Well, we assume that all energy stores have integral causality. There are no causal loops and no causal meshes, if this is the case. Causal paths between resistor ports do not share bonds. If we do these assumptions, then we can automatically, not so important because the computer is programming this, you program this in the computer, you can backpropagate through all the things. Procedure is given here, something for at home, where you generate the state space system directly out of it. Very simple. So basically, step 1, write the constitutive relations of all junctions, write the relations of dissipation elements and storage elements, and then try to arrange this on the right-hand side, which is given by this causal stroke association to each bond. Well, just an example to make it explicit. Suppose we have here our example from before. We have the constitutive relations of all junctions given here with the causal stroke given, the 1 junction here. So I did the causal stroke assignment according to Carnap, which is given here. So obviously I have to look at this 1 junction, UL is equal to that, IC is equal to that, and then I use the constitutive relation of dissipative elements. Why? Because they represent also algebraic relations. Constitutive relation of all storage elements, and with that I associate to everything, introducing the state space variables and do derivative with respect to time of the states. I end up with the state space system. That's it. So it's straightforward, but it's just inserting everything into another. So let's see, this is the wonderful thing. If you look at the storages which are given here, The only thing I have to know is UL. Obviously, UL is given by the Course-Stokes assignment over here. So I just have to insert, and then the state space is is right here. It's down there. It's easy. The only thing again, you have to train it a little bit. But it's not nothing. It's not rocket science. Just well, assigning strokes to something, and that's it. So that's easy. It's just a sequence of or a set of procedures. Well, if this is the case, and at the very end we find the starting point for state space system control design, and that's it. Okay. Second example, our phase-safe hydraulic cylinder. Well, I show you the next slide. Here is the bond graph. Yeah, this is not so funny. And when we first draw this bond graph, well, we saw, yes, it's a little bit complex. And then somebody did the analysis. I think it was a student of one of the semesters before, and he said, well, there is a problem. And I depicted the problem over here. Why? And this is interesting because the so-called causal paths somehow show whether you have a modeling problem. In this particular case, for example, the source of flow, which is representing your pedal or your force, which is pushing against this this piston, is directly determining the capacitance values. So it's not necessary to model this. And we saw that, okay, it's overly simplified in our case. And then I said, yes, perfect. We leave it as it is to show you, okay, this makes analysis easy and understandable. So if you do causal path analysis, you also find something like, well, there might be a problem with the modeling thing. So our bond graph BG as abbreviation is not well posed in this particular case. Okay, and if you look more carefully to that, also the effort and flow variables of L2 is fully defined by the force here. So there is something mysterious about it. So you can ask, what do we have to introduce? Where is the modeling mistake here? This is perhaps something you can answer. Not today, but you can think of where is the modeling mistake? Where is an assumption which we made beforehand, which is perhaps overly simplifying the problem? Okay. Now, again, same question as before. We learned something about the spanning tree, and we learned something about how to determine the number of state space variables. And this can be done with the bond graph as well. So you can perform causality assignment using integral causality as preferred causality. And then you do the very same with derivative causality as preferred causality. And the independent state variables correspond to the storage elements that have the same the preferred causality in both cases. So you compare both cases. In one case, you use for storage elements integral causality. Second case, derivative causality, and then you count the number of states, the number of elements with preferred causality in both cases. Then you have the number of states. And then N denotes the order of the model. Why is this important? Well, again, it's a computational question. So if you have something like Daimler or Simscape, then you know it's something like a bond graph, obviously. And if it's a bond graph, then you can do the causality assignment. The causality assignment, according to this procedure, is fully automatic. can be programmed easy, or has been already. Ooh, we don't have to do it. If so, the computer is able to calculate the number of states by means of this simple procedure, because it does the causality assignment twice, one with preferred causality, incremental causality, once with a derivative causality, and then we know the problem. If you're interested in bond graph theory, there's a bond graph rank defined if n differs from k, if the energy source is higher, but we know this might happen. Now I want to skip this multi-bond thing in a second and want to go, because this is something important later on, but I want to show you what we can do with this notion of bond graphs at the very end, because you might have considered this. Yeah, just a question. You remember this perhaps from multivariable control. This is the Kalman controllability question. So a system, a MIMO system, multiple input, multiple output system, is controllable under the condition that the matrix B, A squared B, and so on, has rank n. This is quite simple to answer. So you might realize, if you do the calculations, if you prepare for exams, then you might have realized sometimes you have the situation where you calculate this matrix, there's a rank drop, and this always happens, very often due to the case that there are zeros inside in the matrix. So, and you learn something like the Kalman controllability and observability structure, so the Kalman separation of a system. And the question appears, what are the structural properties? What happens? What physical properties are there? Is controllability a property which is just with what is just a structural question? So meaning there are some states which are somewhere not driven by anything, whatever value they have. And unfortunately, the answer is really difficult. One can say, well, controllability and observability is a structural property. The system has whatever parameters the elements have, and also depending on the parameters. But we can separate it as follows. For example, we say we define, for example, a structure matrix A is determined by the number and the position of its non-zero entries. So we just look at the entries which are non-zero, and then we make a cross there. And we say this is important. There exists at least at the crosses we can insert everything we want to except zero. Now, suppose you have a matrix which looks like this. Here, 0, 0, and a star, star here. So we can enter 2, 1, or 3, 5, but no zeros. And the question is, if I have a matrix with some zeros and some entries which are non-zero, under which condition I can enter anything I want to in on the elements which are non-zero, under which condition is this matrix or this system controllable or observable? And the answer is given here. A system is structurally first the definition as a system with matrix AB is set structurally controllable, completely state control, if there is at least one numerical admission realization A of the structure matrix A, and the same for B, such that the system is completely state controllable. So what I can end, we say it's structurally controllable if there is at least one realization. And this question, whether a system is structurally controllable, can be answered with bond graphs. And this is interesting because there we see something you might have realized already when you do the calculations with Kalman and all these things. You have perhaps realized that a MIMO system is structurally state controllable if and only if the conditions hold either one or two. For each energy storage and preferred integral causality, there exists a causal path from a control source to the energy store. This means all states are input reachable. To give you an example, back to this example, there's the source, and there exists a causal path to the inductance. Obviously, this inductance is controllable. Obviously, we have this storage is controllable structurally. There exists something. If the gyrator is equal to 0, so the transmission is not there, clearly there's no path at all which hits L, right? So consequently, it's impossible to change the storage behavior in any case. So what I want to highlight with this nice result, and therefore supplementary material, just to give you an impression, there's a lot of theory which dates already back into the 90s, as you see. Oops, one step further, where you see that some of the properties can directly be seen from the system itself, from the physics, from the elements. And this is important of understanding of systems, of system design, if you have this in mind. Nothing for our just what do I mean with supplementary material? Nothing for the exam. So important perhaps for the preparation. I will not ask something in that regard, but it might be interesting for later use then. Well, I think yesterday somebody asked what happens if I have going back, just a simple sorry for the many clicks. Yeah, at the beginning of yesterday's lecture. Yes, here. Somebody asked, why do I have two equations? One equation for the lateral and one for the x direction, one for the y direction. And I said they are independent. Well, okay. Yes. So obviously we have two bond graphs, one for the y direction and one for the x direction. But what happened? This is easy because they are really independent, because due to the perpendicularity of them. Let's have a look at the following simple example. Might be even more complex, also supplementary material. Look at this simple inverted pendulum. I want to show the picture here. If you want to describe this, you can describe the movement of the mass pendulum, moving up and down. Obviously, you need both variables, one for y and one for x direction, for describing the entire equations of motion, but they are dependent because they are moving along a circle. So there are two options, one to make them independent, to say, okay, I just look around the r direction and one on the phi direction, they are again independent. And then I have two independent equations, or I make them dependent because the one direction influences the result of another. Then we speak about so-called multi-bonds, where we have two bond graphs which are somehow connected or can be regarded separately. This is always important if you have such objects where some of their variables which have to be treated independently or more or less independently, and dependence can be treated by means of so-called modulated transformers. So, so the answer again for yesterday's question, yes, we can treat such systems by means of bond graphs, and it helps to describe, well, this interrelation between variables acting on more or less independent domains to make it practical. And then, oops, sorry, to go here. If I do so, I end up with a notation with the so-called multi-bond. That's the only thing you should keep in mind, that sometimes some of the bonds can be stapled together in one bond, as so-called multi-bonds. It's an array of bonds, if you like, and also an array of zero junctions and one junctions. We did something similar for, this is important for some of models we need, also in electrical engineering. Here we have a three-phase power system modeled as a bond graph, which has been done in Felix Ströder's thesis, master thesis, to do a fully bond graph modeling. And then you use the multi-bond, for example, for the electrical system. Then it's possible to do that. Okay, with that, I wanted to stop for today, and hopefully you have a nice afternoon. See you, I think, next week, right? No, next week is